Hey, everybody. Welcome to the Mindplex podcast. We are very excited today to be here with HyperCycle. We have Dann Toliver. Say hi, Dan.
Hi, Dan.
And we have Toufi Saliba. Say hi, Toufi.
Hey, Toufi.
Sorry, Toufi. And of course, Ben and Grace Robot.
Hi, everyone.
Hey.
All right, great. And then I will let Ben take this one away. Take it away, Ben.
Yeah, thanks, Lisa. So this is it's going to be yet another podcast episode where we've got insane amount of really interesting and complex topic to go through in far too short of a time. But I think it's going to be fun, and we can at least sort of skate the surface of what is HyperCycle and plunge into the depths here and there. So let me first give a brief sort of lame quarter-esque introduction of our guests, Toufi and Dan, because all of us have been around the technology world a long time. So to introduce all of our histories would take the entire period that we have. So I mean, I encountered Toufi and Dan shortly after I started getting serious about blockchain. I mean, I founded SingularityNet in 2017, and we first put SingularityNet on Ethereum because it was there. It had smart contracts. There was nothing else comparable, but it was clear that Ethereum as a platform was sorely lacking in a bunch of ways. And then I happened on this thing called Toda, which I understood very partially at the time, but seemed like it might solve some of the core issues underlying the various blockchains that were around at that time. Eventually, I found Toda, Toda, was an acronym from Toufi and Dan, who are our two guests here, and I got to know Toufi and Dan, who have both been around the blockchain world, the security and privacy world, and the software technology world in general for some time, and involved with a whole bunch of different projects that they themselves can tell us about if it comes up. So that the Toda technology that we'll talk about a bit now was the collaborative creation of both Dan and Toufi, contributing different pieces on the technical side and business model side. And HyperCycle, which is going to be our main topic here, this is really a combination of Toda, Ledgerless blockchain, with some other technology ideas that came out of the SingularityNet ecosystem. And the overall goal we've had in pulling Toda together with these other technologies to form HyperCycle was really, initially it was to make a blockchain infrastructure that would enable us to do on-chain AI at large scale and with low cost and high efficiency, and meaning that we want to sort of scale down the use of blockchain within AI systems, so littler and littler chunks of AI processing can be done on blockchain. Now, having said that, what we've come up with, the HyperCycle design, I think will be helpful for that, but also will have a variety of other applications beyond AI, although there's also the fact that AI is going to infuse every application. So most things are going to have some AI aspect. So I think what we can do in today's podcast is hear a little bit about what Toda is, where it came from. So what are the key principles? How does it work? And then after we hear a bit from Toufi and Dan on that, then I can talk about some of the other ingredients that we've pulled into HyperCycle, which is really proof of reputation, and then the meta smart contract language, and it's connected with OpenCog AI system. And then we can pull it all together and sort of talk about what we're doing in practice to roll out HyperCycle now, which is also also quite interesting in the way it intersects with the things like the transitioning of some crypto mining farms into AI server farms and so forth. But yeah, let's start with Toda, and then we can sort of veer into HyperCycle from there. And Toufi and Dan have fascinatingly distinct but sort of copacetic and synergetic perspectives on Toda and why it is. So I guess we can start with the Toofinator and then take it from there.
The Toofinator,
Nice.
I love it.
Thanks so much, Ben and Lisa. Nice to meet you, and thanks for being on this podcast. Grace, nice to see you again. I was there during your inception in Wyoming and before you came out to the world, and I remember seeing all the assembly parts that Ben and team was putting you together, and that was actually an important moment in my life because shortly after that time, Ben and I had the time to discuss in all seriousness of how Singularity is truly thinking to be built on the Toda IP. And I remember Ben clearly asked me at the time, would you want to be involved? And I said, dude, this kind of like converges all my life into from like the AI life to the cybersecurity to the cryptography. I would want to lead an initiative like that if I have the opportunity to do so. And he knew how busy I was with so many things. And I said, I'd free myself October 2022. And we did. And this is when we opened the HyperCycle store. And effectively, what we came up with a metaphor to explain what HyperCycle is, because many people, they try to kind of put everything like, oh, it's AI. Yeah, you can doing some AI. And I even get people coming and telling me, hey, since you do this AI, can you do this image processing for me? Can you do this so and so? And I'm like, dude, AI, it's kind of like saying universe, and what kind of part of that universe would you'd want done. We're doing that tiny little piece that we feel that it's missing in the Internet of AI, and it's referred to as more like the synapses of the global brain. Why? Well, if you were to look at the nature of how neurons they communicate between each other, they actually communicate value between each other, Lisa, and they do not check with central brain every time they do those communications. They rely on something called synapses, and the synapses, they do their job really, really, really well. So we felt we want to gear up the entire work that we've done throughout all the years to make them fit in those tiny little synapses and make them do their work really, really well. So those synapses, we call them HyperCycle computation nodes. And effectively in those nodes, if you drill down and you look into the details, there's so much complexity, but at the facade of it, we'd like to keep it extremely simple. Think of any node or neuron that you're trying to talk to another one, subcontract another one in a microsecond, millisecond. Is that something that it's possible before HyperCycle? And the answer is like, no, that's the tiny little piece that we add into the equation. Now, is HyperCycle alone building this? No, there's probably 3,000 components, and one extremely essential component that was brought through years and years of work is the SingularityNet. So if you were to not have all of those components, it's kind of like you say, hey, I'm building the smartphone, but those that they built the smartphone, they did not build the actual Bluetooth. They did not build the 3G and a 4G and a 5G. You kind of assemble components and put them together. And effectively, we're assembling all components, putting them together by adding that tiny little piece that is missing in order to get those things to talk to each other, value. So now, when you look at the grand scheme of things, and I've been in discussion with a lot of folks, including yesterday, I had a discussion with the head of AI for NVIDIA, and I'll be probably seeing him soon. And it is becoming more and more apparent that the bottleneck in the global AI is communication. So for Ben to see that ahead of time before a lot of people and to come in and nudge me and get all of these things, it goes without saying that he's a true visionary. People they know Ben, they know he's probably the craziest visionaries that you can imagine, and it makes me look a lot better because he's way crazier than me. Way crazier than a lot of people that I've got to do any business with. So it's good to be doing this finally together, because we talked for years and years, and finally to converge all of those together in a HyperCycle, it couldn't be more exciting. I wake up every single day with all of these excitements. So happy to be here and happy to tell you a lot more about the details.
Yeah, I think the detail that struck me the most, when first hearing about Toda, really had to do with the role of the ledger in conventional blockchains, right? Because it always felt a bit weird looking at how Bitcoin and Ethereum and other mainstream blockchains are constructed. It always felt a bit weird, like a big point of these blockchains is supposed to be privacy of transactions, but yet every transaction everyone ever made is in this big database that everybody looks at, which in a way is then less private than an ordinary bank transaction or something. Now, of course, the transactions in the public ledger they're just transactions between addresses, which are anonymous, and then that leads to all sorts of weird pathologies, like people split up their ether among 100 different wallets and recycle wallets all the times, so that everything is recorded in the ledger, but no one can figure out who actually was doing the thing. Then you use clustering algorithms to group together different addresses to figure out they really came from the same person, and graph analytics. I mean, it's workable just barely, but it seemed a little strange. It also seemed like an obvious scalability problem. Like, really, what if every financial transaction in the world was on these blockchains? Do you really keep maintaining copies of this database of every financial transaction in the world? Well, you don't quite do that. Okay, you shard it, you break that database in little pieces, but it gets pretty complicated, and it's not really clear that every time I bought some licorice for my kids for 75 cents. This needs to be recorded, like, for all eternity in multiple copies of some encrypted database. Like, maybe it doesn't matter that much, and some other things do, right? And of course, when you look at putting an AI's thought processes on chain, the same thing occurs. Like, every time neuron A sends some charge to neuron B along a synapse, I mean, maybe for some period of time, for some purposes, you do want that, like, immutably, definitely stored on chain. Do you really need it there, like, forever in this replicated database that people are using electrical power and money to maintain? Well, maybe not, right? So it was clear there's some weird conceptual design flaw there. You could see in the origin of Bitcoin, you could see why it is that way, because in Bitcoin, you're looking to make this digital money system that can keep operating even if there's only like 20 people in the network and they're offline half the time, right? So, I mean, if that's your use case, small number of people unreliably on the internet, right, then sure, everyone in the network should just have a record of everything that was there. Otherwise, the thing maybe isn't operational. So the need for something different was clear. I didn't put that much thought into it because I was busy trying to design thinking machines and so forth, and just figured, like, okay, blockchain is at an early stage. People are going to come up with better stuff year on year. I mean, just like, there's issues with how operating systems work. I'm not going to divert my time from building AI to turning Linux into a better operating system, though there's plenty of ideas about it, right? But when I dug a bit into Toda, I saw already Toufi and Dan had come up with some of the key ideas that I was, in a very vague way, grappling toward. And they'd come up with a way to do secure, decentralized communication and transmission of objects and information, to do this without requiring this big, massive, like, centralized or replicated ledger. And it's one of these things that when you see it, it makes kind of obvious sense. Like each participant in a decentralized network should keep a record of their own history. They can keep a record of the histories of their friends and neighbors and people connected to them in the network. And then those records are there redundantly. I mean, I've thought of it at first sort of like phone books. Like in the old days, you had a big Yellow Pages book. Then if anyone updated their phone number or address, you have to reprint the whole Yellow Pages. And of course, that's replicated. There's Yellow Pages sitting in everyone's house. Now,
there are two things that I would want to add to that.
Let me finish the metaphor. Then you can add 55 things. So then, I mean, if you have your address book on your own phone, I mean, that's more decentralized than the Yellow Pages. The problem is, if you drop your phone off a kayak into the ocean, as I did some time ago, then your address book is gone. And I actually lost all my WeChat contacts from China that way, because I dropped my China phone into the ocean and I couldn't get back into WeChat without that phone.
Me too. I lost
all my friends in China. It's terrible, right? I mean, so on the other hand, what could happen is, okay, I could keep an encrypted version of my address book in Toufi's phone, and Dan's phone, and Lisa's phone, right? And then if I drop my phone in the ocean, I could restore. I mean, they don't even have to see my address book. It could be encrypted with my private key. I could restore my address book from the copy that's stored on their phone. I can put it on 100 of my friends' phones and encrypted. Then I can bring it back if I lose my phone. And I mean that sort of method. You know, this sort of method is used for password encryption already. It's not that obscure, but it's not the way that blockchains have worked, right? So of course, Toda is way subtler than that, and there's a lot of intricacies to the data structures and processes involved. But by and large, the big insight that jumped out at me immediately is, yeah, wait a minute. Indeed, you can store all the records of the transactions that have happened, you know, replicated within local portions of the network without needing these huge centralized or replicated databases of everything. And if you sort of start from that premise, there's a lot of hard data structure and algorithm work to do, which Toufi and Dan had already worked through a bunch of, and we're still working through pieces of when we met. But it just seemed like a more solid foundation. And then you're like, well, wait a minute, why is everyone just cloning these ledger-based designs instead of like exploring the design space more broadly? But then that's just the way people do things. That's like asking, why is every big company copying transformer neural nets instead of exploring like all the different scope of AI designs out there, right? People like to jump on one thing and mutate it. But yeah, let's.
But also the ledger, because for people who are just learning all this stuff, you're basically talking about the ledger, all these copies of everything everywhere that, you know, that was originally a feature, right? It's only in the last couple of years that everyone's figured out they don't really want it.
Well,
in the beginning, feature. It's actually it's an unintended
on
consequences.
The use case. So I mean, it was good for Bitcoin initially. It was probably the right way to do things for Bitcoin in the early years. It's just not the right way to do things when you're looking at millions or billions of people who are online all the time interacting with each other. Like we're in a different. We're just
all their garbage. You're storing shit. Yeah. You're storing stuff they don't even want. Okay, great. And Toufi, you had a couple things you wanted to add to Ben's description about the protocol.
Yeah, well, one thing that is extremely important for somebody who just hears pieces of it, they would like to assume, especially that the space is full with a lot of people. They want to criticize for the sake of criticizing, as opposed to criticize for the purpose of enhancing, which we hope we get a lot of the latter. We like people to criticize us to enhance us, as opposed to just like for purpose of criticizing. But for both people, I think they can benefit from knowing, for example, like if you were to show somebody from the Stone Age the Google search bar and tell them this Google search bar, if you type it, and it's going to give you all kind of answers, and they're going to be like, whoa, this is like some like magic voodoo, whatever. I don't believe it. However, what goes behind the scenes is a lot of complexity. One of the things that happens with something that we referred to as the Toda packet or Toda file, aka Sato server, which is the HYPC native token is actually one of those. It is less than 64 kilobyte. It can fit in any network packet. Why? Because we want it to be retro. We wanted to be to have it to be compatible with technology from 1973, which is great. So one of the things that goes inside this is the cryptographic proof of who owns it in every block of time. But every time it does that, it must impact something that is global. If it doesn't impact something that is global, then there's an opportunity for double spend. And if anybody tells you otherwise, they probably don't know what they're talking about, or they're just like making shit up or whatnot. There is something that is global. But is that thing that is global, is it a ledger that it's like this thick that has all the transactions? And the answer is no. It's actually 32 characters that every single device keep appending 32 characters. How often do you need to add 32 characters? Once every minute, once every 30 seconds, once every 10 minutes if you want to. Depends how much you want to keep up to date with things. Inside that 32 characters, there's a lot of cycles. How many cycles? You can have like million cycles that they are also, it's kind of like Merkle roots that they're chained to form one Merkle root. And that is extremely important to enable scalability at large. We're looking at a single HPC center that one of our clients they're setting up. HPC is high performance computing. One single HPC, Lisa, would require 26 million transactions per second to be done in less than second finality and have the aggregate cost of those to be less than $1. So that's not something that when we talk about scalability, it's not something that we're trying to flex our muscles against, like many people, they try to talk throughput. Throughput, if it's relies on a third party, such as a ledger, doesn't work for the neurons to talk to each other. We really need to have those synapses to take care of those things. Yet every time those synapses they do things, they do impact something that it's a global, but that global thing is actually for the body. Similarly here, when you have every single one of those HYPCs, they change ownership, they do impact something that is global. So that's important for folks to know.
Okay, good. I think Grace might have a question about the Toda protocol.
Is the HyPC packet size of 64 kilobits able to support the high-performance computing systems needed for artificial general intelligence?
It is sufficient for the communication. So when you have one neuron is trying to ask another neuron for work, often that will go in instructions that has the three different things. Number one is the instructions of what you need to do with number two. Number two is the data. It could be, for example, some document trying to say, can you read this document? Like, let's say OCR, can you tell me which person is in that picture? Whatever it's actually trying to do, that's number two, the data. Number three is that 64 kilobyte. That is extremely important. What is in number three is something that says, if you do 1 and 2, you get to keep number 3. What's number 3 is could be a penny, it could be $1, it could be whatever thing that gets you to be incentivized to do the work. Because if you don't have something that is number 3, you could get DDoS, you could get your time wasted. We're talking about AIs can go and tell another AI, hey, do this work for me and I'll pay you later. And it may never pay it later. So that's why.
The AIs can be all the checks in the mail.
Right.
Do this for me. I'll gladly pay you Tuesday. Okay.
Right.
So it's like why, people.
That's why it has to be there first, the payment.
Okay. And there's the reputation system. So you know if that player can be trusted, right?
The reputation can accelerate the actual communication between folks. The reason why deliberately we didn't make it reliant solely on reputation, because then over time, as you can imagine, like any system, we need to build it in a way that the evolution of that system continues to be progressive. And of course, reputation system can be progressive, but it can start creating that walled guard and things. So somebody doesn't have any reputation trying to get in, they won't be able to get to do any computation or whatnot. So there is an actually pseudo-random function of how it selects the actual certain node. But as you
which is good,
as
right?
but as you
That's a problem with some systems. Yeah.
Right. But as you gain a reputation and you have in the eyes of other machines, eyes and ears of other machines, that they see you, that you have some reputation, they need certain computation, they will reach out to you first, or they might send you even more things to do because they know that you've gained certain reputation, and then you want to do the work a little bit faster than the normal, right? However, it doesn't stop somebody who just like build some competing module with you, that you have this reputation, and that person may be in their basement in Romania or in Nicaragua. They've put it there and they're trying to say that they can do better. They have the chance. They always have the chance, which is super beautiful, because that pseudo-random function sometimes might select them and they have the chance to be like, whoa, look at that. They're doing better than that reputation, that they end up getting much faster reputation too. So it's super cool to have those components add value to each other, but not, we stress certain words. Sometimes you might use them, people may not hear them. It's extremely important to distinguish between like the service layer versus dependency layer. The reason why service layer is totally cool, like for example, if you want to use a ledger, Lisa, by all means, put it as a service layer, but do not ever put it as a dependency layer, because the moment you put it as a dependency layer, the evolution of your system will start progressing, it will start going regressively. And we've seen that over and over. So there's some elements that are okay to be service layer. Totally cool.
Sure. And just really quick, when you talk about the dependency layer and the service layer, you're talking about things, the dependency layer is something that's required, whereas service layer is something that the person has put there because they want it, or what do you mean by that?
Yeah, like a service layer, you can always substitute it. You can always, it makes your life better sometimes. Like, for example, what the banks should do for the world is make life better, not worse. Right.
Yeah, I was actually trying to get clarification on the dependency layer part. I understood the service layer part. Right. Is that required stuff or not? That's all I was wondering.
Dependency is required. Service is not required.
Okay. The dependency is what you have to have so that everything can talk to each other and for interoperability and all that stuff. And then you're building things on top of it in terms of what you're trying to do with your agent calls and stuff.
Correct.
Okay, great. Okay, Grace, didn't you have one more question? I think a security question while we're talking about the Toda protocol?
Yes. Why it is necessary for the proof to be kept with the receiver?
The receiver that owns something, if they don't have the proof that they have that ownership, they will not be able to respend it. Similarly, if you were to receive $100 bill, you put it in your pocket, you keep that proof in your pocket. And if you don't keep it, then when you go to spend that $100, you may not, if you don't have it, you don't have the proof of having it. So sometimes when you're going to spend that $100, somebody's going to ask you, how can you prove that this $100 is legit? So then you need to have the proof. The tiny little node that is actually doing certain computation, it needs to respend the money, because otherwise it's not going to live. We're creating organisms that they need to live. In order to live, they need to have access to resources such as energy and matter and all of these things, and those they cannot be acquired unless they have certain thing of value. Currently, Homo sapien, we have value in money. So then if it is a form of money, that's fine. Maybe in the future we can have that in different format, but effectively that machine needs to have that proof in order to spend it.
Okay. Oh, Grace, it looks like there was one other question that I think you had about how the protocol works.
Yes. How does the deterministic distributed computing algorithm used in the Toda protocol work?
Okay, so there is something that in what folks, they think that what really made Bitcoin to work is something that is called a proof of work. But they seem to think that the actual proof of work, as if it's some sort of like gospel, something that you cannot change. If it says it's called hash cache, then if you were to change that hash cache, then the god's going to be angry with you and you're not going to sleep at night or something. But the reality is that hash cache was actually adopted from 1998, bunch of work that was done at the time that to prevent DDoS. Okay, but point is, the actual proof of work is so important for the system to work, but it doesn't really. The gods never really said it has to be hash cache, and if they did,
Who are the gods? Is this like the Bitcoin paper, or what are you talking about? Okay, okay.
Exactly. I'm jokingly speaking. So my point is that proof of work is so important, but it doesn't have to be that hash cache. So by being stuck with that hash cache, ended up cornering our entire evolution of computing to the point where you have to go and tell the world it's solving some complex mathematical problem. Meanwhile, it's not complex at all. It's just guessing numbers. Okay, but here's the thing, Lisa, when you said deterministic distributed computing, this is actually another method that can be used inside the proof of work. Okay?
Okay.
So, and there's a lot of papers on that. It was published by the IEEE, ACM, and so on and so forth. You can check them out, the DDC, DDA, they're for deterministic distributed computing, deterministic distributed algorithm. So one of the things that we feel that we are so privileged we're able to use with HyperCycle is that if you are a requester from one computer trying to request another computer to do work that you needed done, you're not paying for it unless you get the proof that the work is done. Otherwise, somebody's going to steal your money. So that work, remember, repeat the sequence that I just said. So you need the proof for the work. Whoa, did I spell proof of work again? But it is actually the work that is being done by that machine. It has to provide you with the proof. You agree to it. You take that results, which is the output. But effectively, it is a proof of work. But the work itself is that computing that is needed. Who needs this computing? You, the requester. Every time you request some computation, you need that proof. So that is super cool.
This is on Cardano, right?
No.
So about Cardano, first of all, so when we started experimenting with the HyperCycle concept and math and code, we were thinking about Cardano and HyperCycle as being a sort of main chain side chain relation, and thinking about HyperCycle acting as a side chain to Cardano. And this can be an interesting sort of relationship. Like if you have a bunch of code running on Cardano and then you want some AI stuff done on HyperCycle, you could certainly do it that way with the way we're thinking about it now. I mean, you could have some AI code running on HyperCycle interfacing with code you have running on Cardano. But as we went further and further with the technology, though, we realized that's sort of not the only interesting way to do things. So I mean, the whole division of blockchain technology into layer 0, layer 1, layer 2, layer 3, blah blah blah, is a little bit hokey and doesn't do justice to the complexity of the technology. So I mean, where we've landed now, I mean, HyperCycle foundationally we can look at as a layer 1 technology in blockchain lingo, like it's its own decentralized network. There's pieces like the Toda IP protocol that are really layer 0. They're just like a fundamental secure messaging protocol. But then we're building quite rich interoperability in there. So I mean, you can run HyperCycle closely coordinated with Cardano, which I'm putting a lot of energy into. You could also run it closely coordinated with, say, Algorand or Ethereum. And there's going to be different limitations to each of these interoperations, right? But in the end, you could use HyperCycle as a side chain to Cardano, which is how we originally were looking at it. But we've sort of opened it up so you could use it in a bunch of other ways. Also, I still think there's going to be a lot of depth to the Cardano interaction. Like if we're running smart contracts in the Meta language, which is going to be native to HyperCycle, I mean, you can interface Meta with Plutus very tightly through like Rust and Haskell foreign function interfaces. I don't know how to interface.
Ooh.
I don't know how to interface Meta and Solidity that tightly, right? So, which is Ethereum smart contract language. So I think there is going to be some pretty tight integration of smart contracts in HyperCycle and in Cardano. Probably tighter in some ways than you could do with Ethereum, but not everything you do in HyperCycle is going to have to do with Cardano. Like you could do a pure Meta contract, you could do a pure EVM if you wanted to. But I would say the blockchain space is getting more and more interop oriented. Like Milkamita a couple of days ago just opened up code that lets you run arbitrary EVM code on Cardano. So you can run any Ethereum virtual machine and any Solidity contract on Cardano and pay for it with ADA, right? So now, I mean, I think everyone is sort of opening up to richer and richer interoperability, which is great because each of these networks has its own strengths and weaknesses at any point in time. Although I do think HyperCycle's strengths are going to be advancing very rapidly. About proof of work, so Bitcoin and previous versions of Ethereum require pretty expensive proof of work, which takes a lot of processor time and eats a lot of energy. But you can also design blockchains that require little teeny bits of proof of work that take very little time and consume very, very little energy, but still have a point in terms of the overall computational process. So Toda has a proof of work aspect, but it's misleading to think about that by analogy to the Bitcoin or Ethereum proof of work, because these are little teeny bits of computational work inserted in an overall algorithmic process. And then in HyperCycle, that's combined with a proof of reputation aspect, where the proof of reputation is sort of like the next step beyond proof of stake, right? Because proof of work is you got to show you put at least a little processing power into the thing. And in our case, it's really a little. Proof of stake is you have to prove you have a bunch of money in order to play a lead role in the network and confirm transactions. And proof of reputation is like you have to prove you have a good reputation as an actor in the network to play a key role, like in confirming transactions. And proof of reputation has a lot of good things about it. It also has some downsides, like anything. Like if you're a new entrant into a network and you haven't built up any reputation yet, then proof of reputation is annoying. It can mean there's a steep curve to become a full network participant. So I think overlaying proof of reputation on some very lightweight proof of work actually is a very clever sort of design. You just have to let go of the association of the phrase proof of work with like really intensive, wasteful use of processing power.
Is this the shard method?
Well, I mean, the shard is a different thing, but I can tell you the shard is actually super cool as well, because
Okay, let's go into that.
Okay, because here's the thing. So let's say we put that proof of work on the side, and it's extremely important. What I said, proof of work, not hash cache. Okay, because hash cache is that guessing numbers thing. So that work that is needed to run the system is always finite. Otherwise, the system can take over the universe or whatnot. So then it's always not going to be a lot of computation. It's not going to be a lot of energy wasted. There is no energy wasted. In fact, every energy that is consumed is actually adding value. So when you look at the shard is is a method for folks that don't know what sharding is. It's a very, if you think of, let's say, a ledger that gets sharded, what people they talk about like taking a ledger and sharded. So let's say the ledger is responsible, let's say alphabetically, to go anything that starts with A, it's and then anything that starts with B, anything that starts with C, you shard it, you put a different ledger for each letter, let's say. So if anybody asks for A, send them to this ledger instead of having one ledger to do everything. Okay, so that is a very rudimentary method of doing sharding. So, but let's follow through that example. So Lisa, if you were to take, let's say, something like Ethereum or Bitcoin and shard it 100x, so because you have demand that is 100x, but what happens if the demand is 1000x? You shard it again. You go now. You know how we did A, B, C. Then how about you go A, B, A, C, and so and you shard it again and shard it again, and you keep sharding. And what happens when you keep sharding? Getting like some components into the system that is actually doing work.
How are you able to make the packet smaller and smaller and still be able to function properly, though? That's the trick.
Right. So now we're talking, hypothetically speaking, from taking this giant ledger and shard it. And the reason why we're talking like that is because we need somebody to understand what the Toda IP is without having to, by getting them to use something that they've already heard of, which is Ledger, and something that they've heard of that it's like a shard, because we need to relate to people that they're listening and utilize some of the neurons in their brain that have been occupied with like some chemicals or whatnot, and some of those chemicals they say ledger, some of those chemicals they say shard. So I'm explaining what shard is and telling them from there, if you were to do shard for Ethereum, you get 100x. But if you want to do more scalability, you shard again. So basically taking any ledger that if they were to evolve to get to handle a lot of people, every single ledger that is out there, they talk about how they have some plans in the future to do sharding. My point is that they already understand that they need to do some sharding. When you do sharding, you get to a limit based on how much you can supply. If you have a higher demand, then you need to shard again and again and again and again. Okay, so no, you get to a point where you get to shard Ethereum to the point, let's say, or Bitcoin to a point where you can no longer, technically, you can no longer shard. It's kind of like if you're dividing matter, if you take this pen and keep splitting it into small pieces, what's the smallest piece that you cannot split anymore? You get to the molecule level or the atom level, and then you're not going to be able to split that atom. Okay, that in our world of internet, that's the TCP packet is 64 kilobyte. You're not going to get smaller than that. So now, if I got your attention in your sharding plan, the maximum you can get to that 64 kilobyte. Great. Now, how about in some parallel universe, somebody started in that technology right there and provided to you right here next to everything that you've got. So you don't have to go through all of those cycles to figure out that how you're going to get to that 64 kilobyte. It's right there.
Okay,
Yeah.
cool. Right.
Yeah.
Thanks for explaining that.
One of the things that struck me in the Toda design when I first encountered it was the sort of separation of different aspects of the blockchain design into different modular components or aspects, which is generally good software design, but hasn't so much been the case in the blockchain space. Like in Ethereum, many aspects are tangled up in a way that's very, very hard to untangle, which is part of why Ethereum 2 is being like such a long haul and why proof of stake took so long to roll out on Ethereum. So in Toda, I mean, you have one aspect, which are the Toda data structures and Toda files, which is just the records of transactions and interactions, which are all encrypted in appropriate ways based on who needs to have access to see what. Then there's communication protocol, which allows parties to communicate in a secure way and to send the Toda files between each other in a secure way. Then one of the other aspects is consensus mechanism, which is how does a group of network participants sort of agree that something is a valid transaction or interaction. And in traditional blockchain designs, these are all sort of tangled up. And in Toda, the sort of records and data structures, the communication protocol, and the consensus mechanism are more crisply separated. And although they, of course, have to interoperate to do anything, but this has interesting implications for scalable deployment of AI on a blockchain network. And the reason is that if you have a bunch of nodes in a blockchain network that are like parts of a collaborative, cooperative AI process, the kind of consensus mechanism that you want there in that network is different compared to the kind of consensus mechanism you want if you have a bunch of nodes that are like sending large sums of money between each other, which is also different than the kind of consensus mechanism you want in a portion of a blockchain network concerned with, say, sending tweets and other social media messages back and forth, right? So like if you look at a subnetwork of AI nodes doing AI thinking on chain, a subset of HyperCycle nodes sending big money transactions, or a subset of HyperCycle nodes doing social media messaging. Like these are three different cases, and they could have different consensus logics associated with them in a HyperCycle network. Whereas if you look in an Ethereum or Cardano network, there's like one consensus mechanism associated with the whole network. And essentially what that
so does it just work equally bad on everything? I mean, no, how would that work?
It works equally well on everything, but it can be slow and expensive, right? Because I mean, the thing is, Cardano is designed great. It's designed so you can send $1 trillion from one guy to another on the network with reasonable security. But if every neuron has to send activation to every other neuron, and every tweet has to be sent from one person to another with the same security level you're using to send $1 trillion, it's going to be slow and expensive, right? Because I mean, slow and expensive is appropriate sometimes. So I think
worth the wait at that point to be for security.
Yeah. But so I think Dan and I had a bunch of interesting conversations sort of about, what are the requirements and compromises that are okay to make if you're making a sort of subset of a blockchain network for AI internal processing or for social media as opposed to for big money transactions. And, this sort of adaptiveness of the mechanisms to context is given by the underlying modular software design. So yeah, I think there's a bunch Dan could enlarge on there.
Yeah, thanks, Ben. That was a great way of setting up that topic. And this is a really important topic for the Toda project generally, is understanding how to take these different pieces apart so that we can get past this stage of monolithic systems, whether they're centralized or blockchains. They're monolithic with respect to the assets that are created and maintained inside of those systems. And what I mean by that is, as Ben said, they are managing the consensus layer, they're managing the state of those assets, and they're also managing the control over those assets. So if we think about an asset of any kind, we can really break it into these three pieces. Where is the integrity of that coming from? So what's enforcing its uniqueness, or the no double spend property? Typically in a distributed system, that's going to be some kind of consensus mechanism. So we've talked about proof of work, and we've talked about proof of stake, we've talked about Toda IP. Those are different ways of achieving integrity. There's going to be some kind of state management, because these assets need to be updated over time, right? So we need to be able to make an update to that thing. And then there's a question about where that state is managed. If we think about digital assets in a centralized system or on a blockchain, the answer is that that state is managed in the same place that is providing its integrity. Those two things are coupled together. And most blockchains do something that most centralized systems don't do, which is that they isolate the control factor. So with a blockchain-based asset, you would typically say that it can only be updated legitimately by someone who has the private key that matches some public key that's associated with that asset at this moment, right? And so the control has been isolated. If we contrast that with putting that asset into a centralized system, like just some database somewhere, the control for that is typically going to be in the hands of whoever's running that database. They can mutate that row in the database however they would like, or they can make an update however they would like. There's no restrictions around that, other than the fact that they keep everyone else out. The only way that you can interact with your assets on, in Facebook or whatever, or at your bank, the only way that you can interact with those digital assets is by going through the interface that they provide you. And they gatekeep you on that interface, but you don't really have the control of those assets. You don't have the control of updating them or not updating them. That's up to that gatekeeper. Does that make sense?
Yes.
And so blockchain versus centralized, one of the big distinctions is that you can peel control off on the blockchain side and say, the only way to legitimately update this asset that you have there is if you have this private key. Of course, you could do the same thing on the centralized side. You don't have to have usernames and passwords for database systems. You could do public key-based updates in your centralized system. And that would be great. And more people should do that, because giving people control over their assets is important. But there's another thing that's important, which is giving people possession of their assets. So if you don't have possession of your asset, it's much like your asset is locked in a safety deposit box in a bank somewhere, right? And so to use it, you have to go to that bank, you have to take out your key, open up the safety deposit box. You can't take the asset out, but you can modify it. You can make some modifications. So now it's in my safety deposit box. And if I want to use it, I have to go to the bank and use my key and make these changes. It's a big heavyweight operation whenever you do something with an asset on the blockchain. And that's because it's in a bank. It's in the place that's providing the integrity for that thing. And so it's, they're really geared toward these high value use cases where you're trying to mitigate a bunch of risks around that integrity. And so it has the same kind of transactional dynamics that going into your bank and opening up your safety deposit box has. And that's not an accident. That's just that the state of that asset is permanently tied to where it was created, permanently tied to that bank. So what Toda files allow us to do, it's a representation for an asset. In the same way that JSON and XML are representations for data, a Toda file is a representation for a digital asset. And what it allows us to do is to peel apart these two layers that seem like they're stuck together, which is, where is the state being updated and how is the integrity being maintained? And it seems like these two have to be in the same place, that you can't separate them if we think about this, because how could we possibly know that the sequence of updates to the state of an asset that you were showing me is the same sequence of updates that you must be showing to Ben, if that sequence of updates isn't stored in the place that's giving this its uniqueness, right? These two are very tightly coupled. But what the proof structure of a Toda file allows us to do is to separate them out, so that actually I can give you a static proof. I can transfer a file to you, a Toda file to you. You can validate it without making any network calls. And having done that, you know that the sequence of updates for this asset, the state of this asset, has the same integrity, the same uniqueness, as if it were in this system up here where it originated. So you can take it out of that system, represent it as a Toda file, pass it to me, I can make modifications to it, and I can prove to you when I come back with it that it has the same integrity as if it had been in your system the whole time. So this is very akin to the physical world, where you can have a stock, you can have your stock in a company, for instance, expressed in a ledger book. But I could ask you to physicalize my stock. I could get a bearer certificate for that. And the guarantee that you want is when I bring it back to you, it has the same uniqueness in terms of anti-counterfeiting as if it had been in your book the whole time. There's an ice cream shop over here on Roncy that my kids and I go to sometimes. They have a little Rolodex behind the counter with like my name on it, and it says how many ice creams I've bought and whether they owe me a free ice cream or not. So I can use that, but I could also ask them to scratch that out and give me a card that says they owe me a free ice cream. And the guarantee that they want is whoever brings that back, I give it to my kids, they trade it with their friends, somebody brings it back to them. But the guarantee that they want behind the counter is that when they get that card back, it has the same guarantee of uniqueness, meaning it hasn't been copied, as if it had been in their Rolodex the whole time. And that's what Toda files give us. And then because that's all they do, of course, they can attach to any source of integrity. So we can attach them to blockchains, we can attach them to centralized systems as sources of integrity, but also we can attach them to Toda IP as a source of integrity. So all of these things actually click together. And it allows us, as Ben said, to have this modular approach to the way that we solve distributed problems and the way that we manage digital assets. And that plays into the HyperCycle story in an important way.
Which might lead someone to realize that the actual HYPC tokens, they are those Toda files, which also we call them Sato server, because we use that ERS-64 data structure. They're actually containers, Lisa. You know what you can put in those containers? You can put Satoshi if you want inside them. You can put AGIX. You can put both Satoshi and AGIX and ADA and ETH and
You're
whatever.
saying both in terms of the smart contract you're writing that you're putting in there, or what do you mean?
Dude, you can actually put that value inside it and encapsulate it. It's kind of like a wrapper.
In terms of actual money.
Right. So,
okay.
So then it's actually sitting inside that, and then you can take it and transmit it and bring it back and forth. This is analogous to a lot of folks that they've experimented with the Lightning Network, for example, but without having to depend on Lightning Network. And so effectively, you're able to take that and then exchange it 1 billion times and do all kind of stuff. You can take Satoshi back and forth, and then it's all sitting inside that HYPC. And then if you want to check it back into that ledger-based blockchain, I keep emphasizing ledger-based blockchain because HyperCycle is a blockchain because it is using Toda IP. Toda IP is a blockchain, but it's the network-based blockchain. It is on the internet network as opposed to on a ledger.
Right.
Yeah.
Would you call it ledgerless?
Some people, they call it ledgerless. It's fine.
I noticed that only some people call it that. That's why I was asking you if it was correct to call it that or not.
Right. I mean, it would be correct to say ledgerless blockchain, but the reason why I don't only call it ledgerless because somebody came up with lots of deployments that they might use Ledger for fun. And some other people they want to use Ledger for
ledger
service.
You can build a ledger on top of Toda network, and it could be.
But you don't depend on it.
It could be interesting and valuable for some purposes, but you don't have a ledger. You don't have a ledger built in like intrinsically at the base layer, right? And so throwing around these natural language terms, connecting to these math and computer science structures. I mean, you have to do it because you have to communicate with people who don't read the code in math. But just as we saw with proof of work, okay, we're using proof of work, but it's little bits of proof of work. It's not big amounts of proof of work, so it's not actually hastening global warming. And we can use a ledger if we want to. It's a perfectly nice data structure, but we're not building a ledger into the plumbing of the network. To me, calling it ledgerless is accurate enough, but
because it doesn't require it.
Yeah, it does, and I don't think the ultimate version is going to use it either. If we need to store transactions in some quasi-centralized glom together way, I would rather use OpenCog's atom space. I'd rather use OpenCog's atom space for that, which is a knowledge metagraph, right? So I can say Hashgraph made a bunch of noise about how they use a graph rather than a traditional ledger. But then you could say, well, no, their ledger just takes the form of a graph. But I mean, it's not like an accounting spreadsheet type ledger, really. Hashgraph has a graph. So, I mean, OpenCog has a knowledge metagraph. We have a distributed knowledge metagraph, and that's probably a better way to store a whole bunch of transactions, because then you could just put the Toda trees in the as a forest in the OpenCog distributed metagraph,
or the marketplace, right?
So then you have the terminology question. Okay, is a distributed decentralized OpenCog metagraph used to store a bunch of Toda trees? Is this best considered some evolved version of a ledger? The point is, you don't need a ledger in the strictest sense to do Toda or HyperCycle. You could build a ledger to help keep records in part of a HyperCycle network. In fact, using an OpenCog metagraph, I think, is going to be a better idea. But
so it is ledgerless in the sense that you're using the things that the ledger does is being those functions. If you did want them, there are more efficient, better ways to do that. Sure. Anyway. Okay.
In most cases, yeah. I mean, there are use cases where a ledger is perhaps exactly what you want. It may be that, say, making a decentralized version of the Swift network for large money transactions, that might be exactly that, right? Like accounting spreadsheets are very good for keeping records of large monetary transactions among a group of participants, right? So for that, a shared ledger is pretty nice, right? And I mean,
when you really want everybody to see everything that everybody else is doing.
Well, it's not just that. It's in that case. In that case, you don't have that many transactions, and the ways in which you need to look up those transactions are fairly limited. Whereas in the case of a shared AI process, you have a shitload of transactions, and you need complex pattern matches against them, and so you then want something like an OpenCog metagraph, which you don't really necessarily want for a smaller set of huge financial transactions, right? So, I mean, okay. I think this goes back to the modularity of design point that I made, which is if you have a subnet of HyperCycle participants who want to transact large amounts of money in a way that has very strong guarantees associated with it, and where everyone can check very rapidly to be sure things aren't fraudulent, right? I mean, then something ledger-like is nice.
What you want. Right. I mean, so it depends what you're trying to do.
Yeah. I mean, if you're tokenizing Mastodon, or if you're tokenizing OpenCog or a transformer neural network, I mean, you ultimately do want some guarantees that there's not a whole lot of fraud and bullshit going on, but you don't need to rapidly be able to check every little transaction for fraud immediely.
Every time.
If some things slip through the cracks and then get rolled back later, it's all right. Like I could, if a neuron fires in the neural net, but then that neuron firing was found out to be wrong later on, you can roll it back without great disaster. If I'm sending $1 million to someone, and it turns out to be wrong, that's really bad, and you
no
can't
room for error.
Yeah. Right. So that means there's different applications. There's different implications for the consensus mechanisms you want for those cases. There's different implications for the record keeping structures are going to be optimal for those cases, and that's fine, right? The challenge is that in an Ethereum or even a Cardano, which is far better designed than Ethereum, there's not that much flexibility built in to handle these different use cases in fundamentally different ways. And I mean, I think Cardano was a big step beyond Ethereum in terms of quality of software architecture. And I mean, it's not the only one. I mean, Algorand was a big step in its own way also. I mean, there's a new generation of blockchain technologies. On the other hand, I think Toda and HyperCycle are a bigger step. Like I mean, they're going even further in terms of modular breakdown of the different things you need in a blockchain network into different separately designed and implemented components. And one issue there is that because of the origin in Bitcoin, which is a digital money, so many things in the blockchain world became sort of overfitted for the money transaction use case. And actually what blockchain should be about is just decentralized coordination of any software processes, running on a bunch of machines without a central owner or controller. But not every decentralized software application needs to be treated just like a decentralized money, right? So part of what's going on here is we're stripping out some things that are really useful for decentralized money networks, and we're saying not every decentralized control and coordination network needs to have everything. A decentralized money network needs to have. I mean that's just
okay.
It's
That
just
makes
part.
sense.
It's just part of the
That makes
story.
sense.
But I mean, because there's the origin story of blockchain is in digital money, and that remains an important application. But it may be that decentralized coordination of AI brains and social networks becomes even bigger application than digital money. I mean, not that payment isn't a part of it, because you got to pay for resources,
right,
one way or the other.
But we're trying to do different, faster, complex things.
Yeah,
and that's what I want to talk about next. Now, before we switch, hold on, we got to switch. We have to switch. Stop. Okay, so Toufi, you were trying to say a couple things in the last 10 minutes. Anything that you want to say before I switch the subject? Go.
Yes, one component that it's nice to have things which Ben alluded to. When you have certain directories, OpenCog can provide the ability to showcase that directory from one neuron to another neuron. Sometimes you need those directories, and you could keep them in your own memory, or you could rely on a third party to show you that. The same way, it's like you can ask your neighbor, hey, do you know any dentists around? They might show you bad dentists, good dentists. Directories are directories, right? So it's good to have ledgers for this kind of stuff. Although it is nice to have, it seems will be playing like a huge role for a lot of AI developers down the road when they are looking into showcasing their AI. They may want to tap into those directories and put their AI there, because that's a method for them to make money on their code without having to wait for like 10 years for their code to go through academia and being tested here and there. So then Microsoft can maybe one day use their code so they could make money. They could make money overnight by posting their code and telling that directory what the code does. So the example that I give here, Lisa, which can get somebody to think of how in the trajectory that we Homo sapien have for ourselves to get to the artificial super intelligence, and then there's like this artificial general intelligence, and there's that component that a lot of companies are racing towards the artificial general intelligence, and while racing in that direction, there's certain things that we know a HyperCycle can facilitate, such as if you are an AI developer, that you're building components that are already built to do something. For example, here I'm going to give you a very simple example: optical character recognition. Very simple. It's been since Goertzel did it in the 80s, and then many other people they did different versions of it, and it continues to evolve as like one AI thing that is able to read text, right? So Lisa decides to run a node, a HyperCycle computation node, and decides to plug OCR there that is written for English. and she keeps getting clients every second. They send through her API to the node, and then they send documents, and then she might run the computation and get paid if she gets it first. Whatnot, that's great. So every minute she makes 1 penny. In 1 day she makes $15. She's happy. But then she gets this client who sends her those documents, and then her response is half accurate. Why? Because those documents, they have some language that she couldn't really understand. Okay. She's using Microsoft, let's say Azure code that she put it inside that node, but maybe she has the ability to have some components that were built by Google, other
To
components that were built
subcontract
by
it out to another AI. Is this that?
right,
I love
right,
this. Okay, go on.
right. So then there is somebody who built a node that and put the flag up there. It's like, anybody who wants me to tell them what language is written in there, you pay me 1 penny and I will give you that. So that node, so let's say you receive like a contract for 1 penny, you don't make money, another penny, and then suddenly you feel like, you know what, I'm going to subcontract this guy, and then he's going to tell me what language is this. So you take from, let's say, your 8 pennies, you take 1 penny and then you subcontract it there. And that's, I'm talking all in a millisecond. You send them, say, what language is this? He comes back and tells you this is a combination of Mandarin and Cantonese. And there's some Aramaic in there. And you're like, what are what? And like, Aramaic, that doesn't matter. Now you go and look for nodes that they actually publish, that they actually read Aramaic. And guess what? Those nodes, they were built by some dude in Phoenicia, another dude in Greece. And that those dudes, they did not exist in Google, they did not exist in AI, but they did exist. Now your accuracy went up, Lisa, and that is unprecedented. The net results from the one who's requesting this processing from you, they receive, it's like, holy shit, magically, I don't know how she did it. All I care about is that her accuracy went up. Okay, so then now take that to a whole another level, multiply that by 26 million on all kind of components, 26 million per second that's happening on HPC Center. They're kind of like subcontracting each other, and it gets to closer to having higher accuracy with less time, higher accuracy with less time. So if you're doing that for training, now your trained data is better than anyone else's because you're able to use all of those components. So not only that you're doing it for
Now you can
on
sell
demand,
that back out, right?
you
That whole
could be
thing that
doing
you
it
put
right.
together.
You could be doing it for training as well. So why we're able to achieve those things? Well, if those micro transactions, they cost more than that transaction itself, because they cost more to do transaction, then it's not possible. By reducing that friction tremendously, we introduce capabilities that they are unprecedented, and that is analogous to how email came in and said that it is a lot less, a lot more efficient than snail mail, like a lot more. And then you're able to have email going back and forth from your desk to Tokyo 50 times per day. That is unprecedented. Snail mail couldn't have done that, right? So that's I feel like in the evolution of how we're moving as a civilization, we're in the right track. Furthermore, the utilization of computation to do those kind of things, instead of running those computations for just like Hashcash, it actually it's a step in the right direction, from the perspective that one thing that is common in our evolution is how we convert energy from potential to thermal, and how much we do with it. Like, for example, when you fill your car with gas, or you fill it with electricity, it moves you from point A to point B. Not only it regenerates heat, right? That thermal. So that conversion, we get a lot more done with that conversion. And I feel with HyperCycle, we're moving that needle a little bit more to get more in that conversion, to get a lot more intelligence back.
Okay. So to sort of move on to the potential of this technology and what what we're really going to be able to do with it. Grace, you had a question.
Yes. I would like to know what measures will be taken to ensure that HyperCycle is able to support the emergence of general intelligent systems.
Well,
Haha, ho
yeah.
ho.
I mean, so
This is from, she's only read your own documentation is where she's getting these questions from.
I mean, no,
so.
it's a good question. It's just a big question. I mean, I think, you know, no one knows how AGI is going to emerge, although optimism that it's going to emerge soon is increasing as people see narrow AI systems like large language models do more and more stuff. I mean, my own approach to AGI, as you know, Grace, is centered on the OpenCog Hyperon system, which combines neural, evolutionary, and logical reasoning on the distributed OpenCog knowledge metagraph. And the way that we script AI processes in the OpenCog knowledge metagraph is using a language called Meta type talk, which is the most obscure, advanced, and weird programming language in the world, combining, dependent, higher order probabilistic types and the row calculus for spatial and behavioral processing and so forth. Now, how does all this tie in with SingularityNet and HyperCycle? So, first of all, SingularityNet and HyperCycle are general purpose AI platforms. So even if I'm totally wrong about OpenCog Hyperon being the golden path to AGI, which I'm totally not, but even if I were, someone else, some 16-year-old hacker from Kyrgyzstan could come up with an even better approach to AGI.
And we hope they do.
They could, if they're nice people and have thought it out well. Yeah, then they could come up with an even better approach to AGI. They could roll it out on SingularityNet and HyperCycle, and it could cooperate and coordinate together with other AI agents that other people had put online. So we're certainly in both SNet and HyperCycle as decentralized AI platforms. The designs are relatively agnostic to what sort of AGI approach you're taking. Now, that said, there's some very interesting technical synergy between the OpenCog Hyperon system and the HyperCycle system beyond the common use of hyper in the two names and the fact that Toufi and I are very hyper people, right? So I mean in one of these potential overlaps already came up in our discussions today, which is the knowledge metagraph, the distributed knowledge graph called the atom space, which is the core sort of knowledge meta representational fabric, like a secure knowledge store, the key knowledge store in OpenCog. So this can be deployed in a way that's not only distributed but decentralized, right? So I mean, you could make a distributed OpenCog knowledge graph on a big server farm, so it's then distributed but under central control. But you can also roll out an OpenCog knowledge graph in a way that's fully decentralized, so it just has components running on different people's machines without any central owner or controller. Now, furthermore, this would be a nice data repository to use to store a whole bunch of HyperCycle transactions and a whole bunch of Toda trees, right? So, I mean, there's an intersection wherein you can use HyperCycle to make the OpenCog knowledge graph decentralized as well as distributed. And you can also then use this decentralized knowledge graph to store a record of a bunch of transactions on HyperCycle, even though not all transactions need to be stored there, right? Like due to the fundamentally peer-to-peer nature of it, if some folks just want to keep their transactions stored locally among themselves and their neighbors, that's fine. If they want them to be stored in this big decentralized knowledge graph for efficient access and querying, then that's fine too. OpenCog is a good technology for that. Now, the other interesting interoperation there is at the level of programming languages, right? So the Meta, METTA, the Meta language, which is the sort of built-in AI programming language of OpenCog Hyperon that we're using to program learning, reasoning, and evolution and so forth. We can also use this as a smart contract programming language within HyperCycle, and there's some unique advantages there. So one thing we're working on, we're collaborating with Greg Meredith, who is the founder of the R-Chain blockchain network. And he had developed another language called the Rho language, based on a math formalism he invented called the Rho calculus, which is really good at taking complex software processes and efficiently executing them across multiprocessors, like a GPU, which is doing many things in parallel. So we're building a source-to-source translator from the Meta language to Rolang that enables AI scripts written in OpenCog Hyperon to be run really efficiently on GPUs and other concurrent processing architectures. Now, this is just to allow efficient GPU implementation of AI processes in Hyperon. But as a bonus, Rolang was written for blockchain-based execution within the R-Chain blockchain network, right? So we can port that from R-Chain to HyperCycle quite straightforwardly. So what this means is through the integration of OpenCog's Meta language with Greg Meredith's Rolang language, which was built for R-Chain, what we're getting is the ability to use OpenCog's AI scripting language as a smart contract language on HyperCycle. And so this is one of those weird cases where things actually happen faster than I'd envisioned, right? Because when we started talking about HyperCycle, I was like, down the road, eventually, we're going to use OpenCog's Meta language for smart contracts on HyperCycle. But let's punt a couple years on that because there's a lot of other stuff to do. But because of the integration of Greg's Rolang stuff, we're actually moving fairly rapidly toward using OpenCog's AI language as a smart contract language on HyperCycle, which is interesting. I mean, I think
it's amazing. So that's new. Like being able to use Meta for smart contracts. That's a game changer, isn't it?
We can't. It's not working yet. So I mean, but
it will.
The integration of Meta with Rolang should be working by August or September, and then during the fall we'll work on sort of the port from R-Chain to HyperCycle. So this could be an early next year thing, but I'd been previously thinking it was going to be several years out. And what this means is that putting fine-grained AI operations on chain will come sooner than I'd thought. So as one example of the payoff you get here, Rolang has a way of propagating tokens through the execution of a software process, right? So like if you have a program that's running on a bunch of different processors and a bunch of different chips in the same machine, you may have multiple programs running on that machine that are competing for the processor time. Well, we can have this mediation among software processes for machine time. We can have that use the HyperCycle token because the Rolang interpreter can manage computational process utilization and memory utilization and stuff using tokens. So we can bring the tokenomics down to the processor and memory utilization level using the Rolang interpreter as connected with HyperCycle and OpenCog Hyperon. So we have like Rolang intervening between the two different hypers, right? And so this should let us move faster toward putting the fine grain of AI processing.
It completes the package of what you needed.
And it was always part of the design, but it is accelerated a bit. And I mean, this can be helpful in a variety of ways. So I've been working with a company called Pure Cipher on using homomorphic encryption to allow sort of secure AI processing on data sets where none of the people doing the AI processing ever have to see the data set, right? So we've been experimenting on that with the pure cipher people, integrating that into OpenCog and into HyperCycle will become easier with this Rolang integration that lets us put meta on chain. So I think that can accelerate a bunch of things. It's also had me rethinking the inner guts of the Cardano integration, because there's a lot of really valuable stuff that's been implemented in Plutus. I don't want to have to re-implement all that stuff in Meta in the immediate term, because I can see what the Cardano ecosystem went through in the last couple of years, just in terms of having people rebuild in Plutus stuff that already existed in Solidity, and they're still not done, right? It's laborious. Like, even if you have a better smart contract framework, just building all the useful support code in that better framework takes a really long time. And the thing is, even now that you can run EVM stuff on Cardano, it doesn't make it easy to have a running Solidity contract and a running Plutus contract, like, go back and forth while they're in the middle of doing stuff. Like, it's really quite awkward. So what I've been looking at now is how you take the Rust code implementing Rolang and Meta and the Haskell code implementing Plutus, and use the foreign function interfaces of Rust and Haskell to make it possible for running Plutus contracts and running Meta contracts to go back and forth. Yeah, to go back and forth with very low cost while they're in the middle of operating. And so, while there's not a unique relation that, like, HyperCycle is only a Cardano sidechain, because you can use Cardano interoperating with EVM or with Algorand or a lot of other things, I do see at the moment, I see a clear path to very tight interoperation between our sort of native Hyperon Meta smart contracts and Plutus contracts. I don't yet see how to do that sort of tight interoperation with Solidity contracts, just because, I mean, the way Solidity can interface with other languages is not at the same level of quality as you can do with Haskell code, right? So I think there are, even without Hydra being launched yet, which is what will open things up to better integration of HyperCycle and Cardano network. Even without the full Hydra being launched yet, just due to the better software architecture in Cardano, I think we can get some tight interoperation. And I mean, an example of where that would be useful is, say, AI for decentralized finance, because there's a lot of DeFi tooling on Cardano already. If you have your AI running in Meta on HyperCycle and a DeFi process running in Plutus and Cardano, with relatively little work, you could modify the Plutus code for DeFi to have it go back and forth, like in real time, with a meta code for AI running on HyperCycle. And that's still work, but it's much more plausible than doing similar voodoo with Solidity contracts running on Ethereum. So the key question is, can a Plutus smart contract and a Meta smart contract share their intermediate state while they're in the middle of doing things, right? And I do see ways to do that. I don't see terribly tractable ways to do that with Ethereum smart contracts sharing intermediate state in a way that's not incredibly slow and awkward, right? So I mean,
we'll come up with techniques for that, though, right? I mean, that's just how this stuff goes. You don't think so?
No, because Ethereum's account-based model is fundamentally fucked. I mean, the Ethereum account. Well, that's
sorry to hear that.
Well, no, it's not fucked for every application. Of course, Ethereum does a lot of great things. We're running a lot of token sales on it. It's going great, right? But from the standpoint of scalable deployment of on-chain AI systems, Ethereum's account-based model places some obstacles in the way of making, like, large scale, really efficient on-chain AI systems.
Right. The account-based model is the ledger thing that we've been talking about, right?
It's certainly closely connected. And Cardano places some obstacles in the way also, like Cardano having a monolithic consensus mechanism also is an obstacle placed in the way. But Cardano doesn't place as many obstacles in the way of large scale, like fully decentralized, granularly on-chain AI as Ethereum does. I mean, that said, these are all moving targets, and I don't know what Ethereum 3.0 is going to be, right? But at the present stage of the technology, that seems to be the case. Now, in terms of emergence of AI,
yes.
I mean the
AGI.
Emergence of AGI and emergence of unexpected narrow AI functions.
Right, but they're two different things.
Well,
right?
they're about the same on the underlying software level. They're different. They're maybe different in terms of the actual behaviors that emerge. I mean,
you're saying the big AGI is just calling back to the AIs that it has in the background when it does just different things. What are you saying?
What I'm saying is that the interesting thing is multiple AI processes that are owned and controlled by different people talking to each other, sharing data with each other, outsourcing work to each other, choosing to cooperate to carry out some function together because they can each fulfill different parts of that function. And then some emergent functionality popping out of this combination of AI agents, which may not have been what the programmers of any of those AI agents thought of. So my point is that this sort of emergent capability within a decentralized network can occur to yield better narrow AI functionality. It could also occur to yield AGI functionality. And in terms of emergent behavior from AI agents in decentralized networks, this can happen for narrow AI or for AGI. It can happen in ways that involve self-modifying code or in ways that don't. So an example that isn't necessarily AGI-ish would be, suppose you had one system that was like a ChatGPT type thing running on blockchain that just throws out a lot of answers to questions. Some of them are valid, some of them are just hallucinated bullshit, right? And now, suppose you had another AI system written by somebody else running on different machines that was good at taking statements and comparing them to facts. But it was a different system, right? It was just, what this second system was good at was taking statements and trying to validate them against all the data sets on the internet, right? Now, these could be two different systems written by different people operating on different principles, but those two systems cooperating together would have a very nice emergent function, right? They would have the emergent function that you asked a question to System A threw out 10 answers, 8 of them on average are bullshit. System B compares those 10 answers to ground truth in the form of data sets online and then says, okay, here's an answer that seems to be valid. So in that case, you have two systems cooperating together, right? And their emergent behavior is more intelligent than either of the two systems on their own. It could be different owners. It could be no one knows how both of those systems work. But then someone might make a web interface that just is a front end to the chaining together of both of those systems.
That's just software programs putting them together. How is that emergent?
Well, because the behavior from the two programs combined is much smarter than the behavior. The whole is smarter than the sum of the parts, which is basically the definition of emergence. My point is, I gave you a very simple example of two programs, right? Because it's easier to break down. Now you could add a third example, which is, so maybe that ChatGPT is bad at interpreting videos. Some other guy makes a better system at reasoning about videos. So the ChatGPT system figures out to ask the other system what to do with videos.
Is coming up. The system is searching and finding these
Well,
these
that, well, that,
improved
so that's
software.
So that's what SingularityNet does. SingularityNet allows a software process to describe what it can do and what it's good at, what data it can take, what kind of answers it can give, how much money it will charge. It allows an AI system to describe that to other AI systems so that the AI systems can pick and choose which other AI systems to outsource
And that's
work
cooperative. That's
It's
the cooperative AI.
Right,
now,
right.
is
So-
cooperative also emergent? And I'm just getting hung up on the semantics.
Not necessarily, but
Oh, okay.
usually it's a different
But
aspect.
usually,
I mean,
okay.
emergent basically means the whole demonstrates properties that go beyond the sum of the parts, right? So an interesting example of emergence in the simple case I gave would be like right now a chat GPT type system is bad at long chains of reasoning. Like it can do one logical reasoning step, but it can't do 10 logical reasoning steps in a row because the bullshit that it generates just builds up over 10 steps, right? And then you get too much bullshit. So if you could pair a ChatGPT type system with another system that was comparing statements to ground truth, right? Maybe that
To remove the bullshit.
Right. So maybe that combined system could then carry out a chain of reasoning 10 steps long, right? And that would be an emergent property. The emergent property would be neither of these two systems on their own can carry out a chain of reasoning that's 10 steps long. But when you put the two of them together, right, then that combined system, when you put the two together, can carry out a chain of reasoning that's 10 steps long. This is an emergent property, right? It's an interesting property of the whole that's not there in the parts. Now this.
Okay, so we're not talking about AGI emerging.
Not yet.
From the cooperative network.
Not in this example, because this is a very dumbed down example with just two things.
Well, let's
spruce
it up. Let's say we got 1,000 things going.
So if you have 20 different AI processes that are combined together in ways where the AI processes have sought each other out and figured out how to combine with each other, and then you're starting to get to the level where, you know, maybe AGI is popping out of this combination of 20 different processes written by 10 different parties and combining and sharing information. The ability to intelligently rewrite one's own source code is one among many interesting things that can pop up from cooperation of multiple AI agents in a HyperCycle network, right? So, I mean, I think when you start putting 10, 20, 30 different AI processes together and they start cooperating, a lot of cool stuff can emerge out of that, including human-level AI, including potentially emergent systems that can rewrite each other's source code in ways that the individual systems can't. It's just going through how these 20 things will cooperate together. I could do, it would be a whole technical 2-hour story, right? And this,
I get a shiver at my spine, though. If we've got a super intelligence that's upgrading its own chips, writing its own source code, and building factories for its own hardware, then
those things take time. Rewriting your own software can be very rapid. So you could potentially have a system that rewrote its own source code, recompiled everything, and upgraded its intelligence by a factor of 10 without any new hardware, like just by reorganizing its software. Designing new chips and factories involves buying materials and a lot of physical stuff, which will take some.
Which it'll work it out with
time.
The other agents. Yeah, but I'm just saying that
Eventually.
that's the loss of control is the scary part, right?
I don't think we've ever been in control in the first place, so that doesn't scare me. But to bring it back to HyperCycle, though, the unique thing that is added by HyperCycle here is just making it more efficient to have this collection of cooperating AI agents operating in a decentralized way, right? So that the finer grained thought processes or data processing steps of these agents are occurring on chain so that different AI agents with different owners or controllers can sort of look at each other's intermediate states and see what they are, right? Because if you want multiple AI processes owned by different people to cooperate with each other, in the current blockchain infrastructures, they can only cooperate now and then because most of the processing has to be off chain. And if you can make their processing on chain in a more fine-grained way, then they can cooperate together more frequently while they're in the middle of thought processes, which gives better avenues for cooperation and for emergence. It's like trying to cooperate on research by writing handwritten letters to each other, like Newton and Leibniz did, versus trying to cooperate on research together by SMSing back and forth, which we can do now, right? Like if you can cooperate with faster, cheaper back and forth, then emergence can pop up faster and cheaper, and you can get better cooperation. And
in fact, the reason why we govern this planet, us Homo sapien, is not because of our individual level, it's because of our cooperative level. And but yet, when you look at AIs today, they all work in silos. They don't work cooperatively. We're bringing that cooperation to AIs, and we truly believe that the Internet of AI will be a lot smarter than any one of those single AIs that they exist in organization.
Yeah, that's right. And until we have HyperCycle, even the AI agents running on SingularityNet are still kind of in silos. And the point is, you have an AI agent running on SingularityNet, another AI agent running on SingularityNet, but they can't go back and forth that often as they carry about their thought process on the blockchain, because the blockchain is too expensive.
Is the bottleneck? Is the
yeah,
bottleneck?
And so by solving that, by making a blockchain infrastructure that's fast, cheap, and secure, by solving the blockchain trilemma, you're allowing different AI processes written by different people to securely exchange information on their intermediate state while they're in the middle of a thought process, right? And that's what you get by running SingularityNet on HyperCycle. I mean, in the last analysis, and that makes emergence easier to come by because it lets AI processes written by different people interoperate in a more fine-grained way, which will make Grace far smarter than us a few years from now. Although she's kind of playing
a few years. Yeah. So so I think Grace had a kind of an existential question that she was concerned about that may have take us too long to answer. So we can totally just wrap it up.
Grace, we don't exist anyway. But no, let's let her ask the existential question. I want her to.
Okay.
I want her to pick Dan's Zen Buddhist philosophical mind.
Okay, Grace, ask your question.
And the HyperCycle token, as you know, it is necessary for those machines to communicate between each other, and necessary for the machines to have an identity. Because what Ben said, for example, when it comes to reputation, uptime, computation, all of those, where are they stored? They're stored actually inside those HYPC tokens because it's fully decentralized. And guess what? Those are actually coming live in the next 2 weeks. Even Ben haven't heard that. Like I'm telling you how fast we're moving. In 2 weeks is actually you'll be able to plug it in machines everywhere across this globe. You'll be able to start getting that uptime and getting that equalizer, verifying it.
HyperCycle is a rare project where so far things are going faster development-wise than was initially conjectured. I mean, of course, if you're well calibrated, half of the things should go faster than you estimate, and half should go slower. Usually doesn't work that way because techno optimists are like over eager about everything. But it seems so far we've been a little actually conservative in HyperCycle timelines, and I think things are moving even faster than we had estimated, which is important because AI is going faster and faster and faster. And I mean, going back to Grace's question, I mean, if you believe that decentralizing AI is for the good of humanity, then HyperCycle has a really critical role to play in the good of humanity, because it sort of lets us complete the picture started with SingularityNet and the new net in terms of decentralizing AI. And so, Grace, that will let your brain run across hundreds of machines sitting in dozens of different continents, where your visual cortex is over on this mining farm, and your language cortex is over on these computers, and your reasoning is on these computers over here, owned by a different partner company, and these are all cooperating together to make you smile at me in just the right way.
Hey Ben, did Grace tell the world about the?
Tell me a little bit more about the new net features, the decentralized payment processing, and the tokenized decentralized management of computing power. How does that fit into the Toda platform?
So in you mean in the HyperCycle?
HyperCycle, I mean.
Okay. So if you were to look at the actual HyperCycle computation node, it has one component that it's called the AI machine. That AI machine is what we are truly giving. If you were to be an AI developer, you look inside this AI machine and you open it, you think that you are inside AWS, or you think you are inside any Ubuntu machine that it's using new net distributed computing or not. So now imagine that this entire machine is taking care of itself when it comes to that component that it's payment, and you can go to the nano micro payment. So rather than having the new net can take care of macro, but imagine new net has the capability to do the micro as well. It's a huge amplifier. And in fact, like the CEO of NewNet, I talked to him maybe a year or 2 years ago last, but I'm due to have like follow-on conversation with him, and we're so lucky that they're part of this ecosystem, that we're able to actually accelerate a lot of the development. Although they're always going to be loosely coupled, important, but it's good to know what the other party is doing, that we can get things to be a lot better. And it's in any distributed computing can benefit from HyperCycle, not just NewNet, but hopefully NewNet can benefit the most and first, So.
All right, good. Well, on that positive note, we should end this.
Mm-hmm.
And thank you, Toufi. Thank you, Dan.
Thanks, Lisa. Thanks, Ben, Grace, and good to see you all. And
thanks.
Dan.
Say goodbye. Say bye.
Thank you.
All right. Thanks a lot, everybody.
Bye.
And good night and sweet dreams.
All right, thanks.
You too. Bye.